All right, so this is the third video of this updated statistics series. Um, so let me very quickly just make some room on my screen. So I'm going to move this graph up and out of the way. Now, this is something we could copy and paste into our lab report or IA. But what I'm going to show you in this video is how to do a t-test. And a t-test, as you read, is a statistical test that's going to compare two groups um, to see if the difference is strong enough. And what it actually does is calculates a t-value using a formula that you don't need to worry about. You just need to know how to do this for your IA. But doing a t-test, so you get a calculated t-value, and then using that calculated t-value, you have to compare that to what we call a t-critical value or a t-table value, which is based on a probability level and the degrees of freedom. Now, the degrees of freedom is based on the number of data points that you have in the t-test. So in this case, we have 10 data points in each of the two data sets from before and after the exercise treatment. So it's going to take into account the number of data points and their means and standard deviations, whereas what we were doing before with the mean and the standard deviation and graphing it did not take into account the number of data points. So a t-test is going to give us a little bit a better understanding of there's a statistically significant difference between the data points or not. Now, there are a couple ideas that we need to know, and that's the probability level. In science, the minimum confidence level that we need to know, to make any kind of claim is a 95% confidence level, or a probability level of 0.05 or 5%. And that's a 0.05 level that whatever difference exists between the two treatments, or two independent levels of the independent variable, is by chance. And so the lower that number, the lower that probability, the higher the probability or the lower what we call the p-value, the better. But the minimum amount is a 95% confidence level, which translates to a p of 0.05. So let me do this, and we'll come back to those ideas if you're lost. So the first thing that I need to do is actually put in an add-in. So if you follow my instructions, you'll be able to do this on Excel. And most of the time, you only have to do this the first time. Although if you're doing this on the school computers, you may have to do it each time. I'm not sure if the settings stay. But if you click on File and then go into Add-ins here, oh, excuse me, not add-ins, you go to Options and then Add-ins, let it load. What we want here is the Analysis Toolpak VBA. So if you click on that and click on Go, don't click on OK, click on Go, because what this will do is open that toolpak. And then what we want to do is, actually what I do is click the top two. I don't worry about these two, and click OK. Now what you'll see pop up, if you click on Data, there's a new button over here that says Data Analysis. And that's what we wanted. That's what's going to make our t-test function a little bit easier for us. So I'm going to go ahead and click on Data Analysis. And I'm going to scroll down to my t-test. Now if you notice, there are three kinds of t-tests here. Now my data set, you need to know a little bit about how the data was collected to figure out which kind of t-test to use. In this case, I'm testing the same individuals before treatment and after treatment. So I'm going to click on Paired to sample for means. But if you are testing a different set in each of the levels, so if I tested different bugs in the two conditions, two different sets of individuals, let me clarify, two sets of individuals of the same species in the two levels of the IV, I wouldn't be using a paired, I'd be using one of the other two. These are actually unpaired, even though it doesn't say unpaired. Now, I would recommend that you always go with the unequal variances, and that's going to save you and cover you and give you a better analysis. But for this case, I know it's paired. So I'm going to click on paired, click OK, and I have here two fields to fill in, variable 1 range and variable 2 range. So I'm going to click on the variable 1 range blue button over here and click on my data sets. But notice this time I'm putting in the title. I'm putting in before as part of this data set, and with variable 2, I'm going to click after and down to the bottom data point. Now, because of that, I am putting in the labels. I'm clicking labels, which indicates the top row is labels, which will help me make sense of the data once it puts it out, the data analysis. My alpha is 0.05. So that translates to the probability of 0.95 or 95%. So this is going to give me a much better confidence level, the minimum. And if you wanted to test to a higher confidence level than 95%, let's say you want to test at 99%, you'd put in 0.01, and then you'd have more confidence in your data. But we're going to stick with 0.05 and see if there's a difference. Now, I don't want it on a new worksheet. I actually want it on the same worksheet. So saying output range, and I'm going to click a cell, let's say down here, click this gray button again, or blue button, and then hit OK. And it'll process, and I got all this data. I'm going to scroll down a little bit. There's a lot of data here. And there's some of it that's important for me. Well, we got the mean, 63.9 and 84.1. That's what we had up here, but in our earlier video, we rounded that to match the decimal points that we had in our raw data. So that's useful to us. We see our variance is different. So I'm going to delete that because we don't need that. We've got 10 data points from before and 10 after. And I told you that's important for the degrees of freedom. And that's indicated here with DF. So I don't need this anymore. I don't need the Pearson correlation. My hypothesis, or my hypothesized difference, mean difference, is 0. And in statistics, we can't prove things in science, so instead we disprove things. So in statistics, we call that a null hypothesis. Or in other words, that there is no difference between the two sets. And if we try to disprove that, then we're supporting the idea that there is a difference. It's kind of backwards, but that's the way we have to do things in science because we can't prove things with 100% certainty in science. So my hypothesized mean difference is 0, but I don't need that. That's assumed already. We understand that. Now our degrees of freedom is 9, which is important to indicate in our IA, and this gives us some other data here. Now the t-stat, I'm going to relabel this as my calculated t-value. Let me open this up a little bit. This is my calculated t-value. So that's really important. I'm going to highlight this because this is important. And so is this. Degrees of freedom is great because it actually allows us to figure out what t-critical value to use. Now, I'm going to tell you that we're always going to look at two-tail. T-critical, two-tail. So this is what we need right here. Okay, so we definitely don't need this. And I'm just going to leave this here to talk about it in a second. But if we compare our calculated t-value to our critical value, so negative 8.1 to 2.26, we see that our calculated t-value is less than our t-critical. It's less than. So what that means, if we know that relationship, that calculated is less than t-critical, that means that there is no significant difference. Notice I didn't say insignificant difference. That's not a word in statistics, insignificant. Instead, we say there is not a significant difference between the data sets. Now, wait a minute. You might say, well, look at this graph. It shows that. But remember, that's at one standard deviation, and it doesn't take into account the number of data points that we put in. So the t-value is the most statistically sound test when comparing two groups. So when we do that, we see that our calculated t-value is less than our t-critical value. Now you could use, so this is calculating it. You also should double check this with the table that's in your textbook. Because sometimes Excel has a funny way of calculating degrees of freedom, which isn't actually statistically sound. So you want to be able to calculate your own degrees of freedom. You can double check it. If it's the same number, then your critical value is going to be correct. But if your degrees of freedom is off, then you need to use the t-table to follow to see where the intersection is between the correct number of degrees of freedom and the probability value of at least 95%, or alpha of 0.05. But just as another rule of thumb, any negative value here for a calculated t-value is going to be less than the t-critical value, no matter what the number is. If it's negative, it's always less than. So if you look at the t-table, you'll notice there are no negative numbers on the t-table. So it's easy to figure that out. But you can use this as part of your analysis and your conclusions for your justification for your conclusions for your IA. Okay, so that's how you do your t-test. You can take these values and put into a chart, a nice clean chart that's clearly labeled, that your mean has units on it. Your standard deviations should have units as well. Your t-value does not have any values. Doesn't have any units. It's just a t-value. Okay, so that's how you do a t-test, and that's as far as you need to be what you need to be able to do for statistics.